I'm trying to walk you through using Matlab and the symbolic toolbox to explore Laplace transforms. Okay, so this is from the live editor. I pasted in the table for properties of Laplace transforms so that if we need to go back, we can take a look at these tables. I also pasted in common Laplace transform signals so that we can check our answers that we get in Matlab to see how this all works. All right, so let's get started with that. I'm going to go and I'm going to first of all, and I hope you open up Matlab and follow along and do these commands. I'm going to open up Matlab. I'm going to define some symbolic variables. I know I'm going to use the Laplace variable s, the time variable t. I might use a, b. I wanted to show you that you can use Greek letters as well. So defining some variables. All right, so next, what I want to do is I want to, let's make a signal x, and let's make it e to the minus at. Okay. All right, so I've entered that in Matlab, and I want to take the Laplace transform of it. Okay. I don't hit a semicolon so I can see the answers reported back to me. I go up here and hit run, and I have this configured to show up underneath our Matlab commands. All right, so sim.sim. Okay, and so we can see x equal exp minus at. It puts that into a more typeset form. All right, and I can look at the Laplace transform, and it matches with the table. It's a plus s, but that's the same as s plus a. So I go back into the table and take a look. And indeed, I feel good about that answer. Okay. So if I wanted to change this to t times the exponential minus at, rerun that, what I'm expecting to see is s plus a squared. And I'm starting to notice these patterns. If I have a repeated root, I get this polynomial t times e to the minus at. All right. So what do you predict would happen if you had t squared? All right. Well, you can see. And whenever you add a polynomial term to the time domain signal, it repeats the distinct and real, the real root down here for the Laplace transform. Okay, well, let's explore a few others. Let's do, let's say, cosine omega times t. Right? I run that, and what I wanted to show you, Matlab does substitute the Greek letter omega into the expression, so that's kind of nice. And we get our transform s over omega squared plus s squared. So checking that with the table, yeah, that looks consistent. S is on the top, s squared plus the frequency term squared. All right. So that's looking good. What do you suppose would happen if I multiply by t? Right. So I run this, and what I see is I get a couple of terms here. Okay, I have the usual term that looks like well, let's see. I guess that pair doesn't show up in the transform table. I thought I was going to be able to match that with something in the table, but it doesn't match. But the point is, if you wanted to multiply t times cosine omega t, you can use this to calculate the Laplace transform. Okay. One other thing I wanted to show you before I leave this video is what if we wanted to go the other way with this? Okay. So let's say we had a capital X, and I said that was going to be 1 over s plus 5 times s plus 2. Right? We haven't talked about how to do this kind of inverse yet, but you may remember it from differential equations. Right? So when sorry, I hit the parentheses here wrong. So 1 over quantity, s plus 5, s plus 2, I have the bracket here. All right. So when I run this, I want to get the inverse Laplace transform. Now, I'm given this Laplace transform, I want to get back in the other direction. So I put I Laplace for I is for inverse, and we rerun this and see what happens. Okay. Oh, I put the wrong. He wasn't able to do that, so I had an error. Okay, so you see, it actually did this. You may remember from differential equations that to solve this, you would have needed to do a partial fraction expansion. We'll cover that in another video. But it was able to do that and get the answer. All right, so I wanted to show you this so that you can play around with Matlab to take some of the tedium out of exploring Laplace transforms, because the concepts are fairly simple, but you need to learn how to manipulate things so that you can look at control problems from an input-output point of view. And I think that's easier to do when you use Matlab.